representing a binary digit. In fact, you can kind of see it in that word, binary digit. You can just shorten it to bit. So that bit can be either 0 or 1. So if we allow ourselves a different number of these bits, we're going to get a different computer programming class here. These may be terms that can either be north or south. It's like a numeral video was appropriate programming, cybersecurity, IT, and related sorts of disciplines. So if that doesn't really apply to you, you might need to find whichever video was appropriate for you. That being said, if you want to learn about binary, this is exactly where you can do that. So we mentioned this in the previous video. A binary numeral is a base 2 numeral. We are very limited in what we can do in binary because the only digits that we are allowed are 0 and 1. But binary numerals, when it comes down to it, is pretty much the basis of everything in electronics, because anything that can be represented with two different states, like a circuit that can either be on or off, or a statement that can either be true or false, or say magnetic poles that can either be north or south, any one of those two separate states can be represented in binary. I'm going to throw in a little bit of computer verbiage here. These may be terms that you're familiar with. In fact, you might be more familiar with them than I am, because you might do a lot more computing than I have in the sort of 3 or so programming classes I've taken in my experience. But one of the sort of basic building blocks in computing is a bit, and a bit is the smallest unit of storage in a computer. So a bit is a way of representing a binary digit. In fact, you can kind of see it in that word, binary digit. You can just shorten it to bit. So that bit can be either 0 or 1. So if we allow ourselves a different number of these bits, we're going to get a different set of binary numerals that we could represent. So if we allow ourselves only one bit, well, we've just said the only possibilities we have are 0 or 1. All in all, that is 2 possibilities. And oops. And if you'll allow me, I know it's not a binary numeral here, but I'll go ahead and represent that number of possibilities here as a decimal numeral. Of course, when we see a 2, we know it's definitely not binary. Now, what about if we went up to 2 bits? So if we have 2 bits, we have 2 positions that we're working with, right? So let's think about all the different things that could take place in those positions. We could have zeros for both of the bits. Or we could have a 0 for the first bit and a 1 for the second bit, or vice versa. And this is actually a different possibility. You could have a 1 for the first bit and a 0 for the second bit. And then lastly, we could have a 1 for both bits. So then, all in all, that'll get us 1, 2, 3, 4 different possibilities that could occur here. And now as we go on to more and more bits, we're going to see more and more complexity here, because if we're trying to think about all the things we can do with 3 bits, well, let's start off with the possibility of everything being 0, right? So each of those bits could be 0, or we could have the first 2 being 0 and then the third one being 1. Well, let's just try to list all the things that could happen with a 0 as the first bit. Well, again, note the second and the third bits could be just like they were before, right? 1 and 0, or they could be 1 and 1. So basically what we've done here is we've just tacked on a 0 to all the possibilities that we expressed above. Well, we could do that, or we could tack on a 1 to all the possibilities that we expressed at the previous step, right? So we could have a 1 followed by 2 zeros, we could have a 1 followed by a 0 and a 1, we could have a 1 followed by a 1 and a 0, or we could have a 1 followed by a 1, 1. How many possibilities do we have? We got 4 there and another 4 there. So that tells me with 3 bits, I can express 8 different possibilities here. Now, in the previous section, we talked about how to go from a binary numeral to a decimal numeral, right? So all of these things are base 2. Remember the way that we wrote that in the previous section is we put that radix in there. So when I put that radix down there, well, this one's kind of boring, right? If each one of those is 0, I don't really have to think about doing the base expansion, right? That's just nothing, right? So what about if I have 0, 0, 1 in base 2? Remember, the rightmost digit indicates the numerical value, just its own numerical value. So we got nothing from here plus a 1 from there. So 0, 0, 1 in base 2 means 1. And let me go ahead and put this in base 10, just to be very explicit and clear here. The next one that I wrote, 1, 0, 1 in base 2, well, we mentioned that that's just taking its own value. The number here is times the base to the power of 1. So that's just going to be 1 times 2, or just 2, again, in base 10. Continuing on in this fashion, right, if we have a 0 and then a 1 and then a 1 in base 2, that first, or sorry, the rightmost digit is a value of 1. That digit is a value of 1 times 2, so this is 2 plus 1, or 3 in base 10. Going further, oops, I've ran through my first 4 possibilities. Let me go to the next one, which is 1, 0, 0 in base 2. Remember, this digit here is being multiplied by the base to its index. Its index is 2, right, because we're going 0, 1, 2. So this is going to be 1 times 2 squared. So that's equal to 4 in base 10. Continuing on, right, this thing here, well, we don't have to go through this whole process with the base expansion. We start to get better at this, right? We know that that digit represents 4 from what we just said. That digit represents 1 from also what we just said. So that means it's going to be worth 5 in base 10. 1, 1, 0. Again, this thing is worth 4. This thing is worth 2. So this is worth 4 plus 2, or 6. And then the last one, we have the 1, 1, and the 1. This one's worth 4. That one's worth 2. That one's worth 1. They are all activated. So 4 plus 2 plus 1 is 7. So this is worth 7 in base 10. So actually, the order that we happen to write these things in is actually just counting in binary numerals. This is 0, 1, 2, 3, 4, 5, 6, 7. That doesn't look like it, but that's the number that's being represented with each of those numerals. Well, that was what we did for 3 bits. What could we do to figure out how many different binary numerals we could make with 4 bits? We kind of already described the process above. We could take all 3-bit numerals and then put either a 0 or a 1 in front of all the possibilities. So if we put a 0 in front of all of these possibilities, well, we've got 8 of them. So we've got 8 possibilities if we did that. If we put a 1 in front of all of them, well, again, we got 8 possibilities, so 8 more possibilities. Then that would tell me a total of 16 possibilities. And by the way, that's a number in base 10, so go ahead and write that as a decimal numeral. So we got a total of 16 possibilities. By the way, right here in these 2 examples, we have just illustrated why octal base 8 and hexadecimal base 16 are going to be particularly useful here, because here we know that with 3 bits, we could describe 8 possibilities. With 4 bits, we could describe 16 possibilities. All right, so now the next thing we're going to do is continue this pattern, right? If we kept allowing ourselves more and more bits, how many different binary numeral possibilities would we get? Well, what was the pattern that we just did before? How did we go from 8 to 16? Well, we doubled that because we saw that with the previous system, we could either have a 0 or a 1, right? So that's going to double the number of possibilities that we have. So here is going to be 16 times 2. All of these are going to be decimal numerals, by the way. So 16 times 2 would get me 32 possibilities if I had 5 bits. If I take that and double it, that would be 64 if I had 6 bits. Take that and double it. That would give me 128 possibilities if I had 7 bits, and then 128 doubled would give me 256 possibilities with 8 bits. Well, what if I had n bits? How many possibilities would I have? Well, at this point, we're going to have to think about the pattern that's being exhibited here. The 16, how did we get it, right? Well, we had 2 times 2 times 2 times 2, right? From that previous page, right? Each step doubles the number of possibilities we have. So the first bit can have 2 possibilities, and then same with the second bit, third bit, fourth bit, or whichever direction you want to count that. There's a better way to note this, right? When we see 2 multiplied by itself a total of 4 times, that's 2 to the 4th. So 32 is 2 to the 5th, 64 is 2 to the 6th, 128 is 2 to the 7th, 256 is 2 to the 8th. So if we had n bits, we would represent 2 to the power of n different binary numeral possibilities. So that word bit shows up a lot in computing, like an 8-bit video game system, like the Nintendo Entertainment System, for instance. Another very common word that we use is a byte. So when we're talking about storage, we often talk about like a gigabyte or a megabyte, right? So a byte is going to be equal to 8 bits. And most times when we measure computer memory, we are talking about a number of bytes. So, for instance, 8 bits, one example of a byte would be 10010111, which as a human being is kind of hard to read. So the way that we might represent that to make it easier for our eyes is we'll split it up into 2 groups of 4, 1001, 0111. It means the exact same thing. There's no substantive difference. It's really just makes it a little easier to parse. One more little technical word here, which is actually a word. So the definition of word in the context of computing is the number of bits that are handled in one instruction for a particular device. So a device is going to read a certain number of bits, and then based on that, it's going to execute some sort of computation, basically. So most modern computing systems are 32-bit or 64-bit, right? But previous like gaming systems, for instance, operated on a smaller number of bits. And having more bits gives you more possibilities in a way that grows at an exponential rate. So when we allow ourselves more bits, it gives us quite a great deal more sophistication. So let's just look at how many possibilities. How many different binary numerals could we represent with 32 bits? Well, from the principle that we just did above, n bits is 2 to the n, so 32 bits would be 2 to the power of 32. Now, 2 to the power of 32 is a rather astronomically large number. It is 42949679296. So many digits that we have to start thinking about putting in commas like this. So this is about 4 billion and change, which you'd think would be enough for pretty much anything. Turns out, not necessarily. We'll see this in a future section. Now, when we go up to 64 bits, you might think, oh, twice as many bits, that should be twice as many numerals, right? Well, note, that's definitely not the pattern that we saw above, right? When we add 1 more bit, it doubles the number of possibilities. So when we go up to 64 bits, we have 2 to the 64. This is a number that is too big for your calculator to give you all of the values for, but I'll just let you know what it is approximately equal to. It's roughly equal to 1.8 times 10 to the 19. 10 to the 19, that's really, really, really big. What that's roughly equal to is 18 billion billion. Or 18 billion billions. Those are those numbers that are so large that it is nearly impossible for the human brain to understand them. But this is, when we say a 64-bit computing system, it means that each instruction could be one of 18 billion billion instructions that would be possible in that system. Again, having these higher number of bit of possibilities is actually really important for things like cybersecurity. I'm sure you'll learn a lot more about that in classes taught by people who know more specifically about that discipline. So computers are, on a fundamental level, built in binary. So circuits that are either off or on, transistors, right? Those things here are represented. Each of those little tiny, 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 tiny pieces can represent one of 2 states, off or on, 0 or 1. But the problem is that most people using computers don't necessarily think in binary. If you spend enough time with it, you probably could. But one of the things that we need to do is be able to convert in between that binary system and the decimal system. Well, we actually did this already. So let's look at that number, that binary numeral we had before, and convert this into a decimal numeral. Well, let's remember the deal with each of these things, right? We have an index. We've got 8 different digits. Index starting from here. So the index is going to be 7, 6, 5, 4, 3, 2, 1, 0, right? Because we had 8 of them. The rightmost one is 0, so we have to start counting down from 7. So that is going to be the power of 2 that we have here. So this number, when we represent it as a decimal numeral, the first digit 1 is being multiplied by the base, right? The binary numeral here. It told me it was a binary numeral, so we got a base 2. So 2 is being taken to the power of the index, which is 7. And then 0, we decrease the index by 1 and keep going, right? This next 0 is also multiplied by a power of 2 that is 1 less than the preceding one, and we keep going. We've got 1 times 2 to the 4, 0 times 2 to the 3, 1 times 2 squared, 1 times 2, ran out of space, and then this last one is 1 times 2 to the 0, or just 1. Note that now it's really helpful for us to remember what these powers of 2 are. So if you spend a lot of time working with computers, learning your powers of 2 is definitely going to be valuable. So this first one has a decimal numeral of 128. That's nothing, that's 16, that's nothing, that's 4, and then 2, and then 1. So let's see, what do we got? 130, that's 20, that's 150, so 151. Just to make sure it's absolutely clear that that's a base 10 numeral, we'll write that 10 in the bottom right-hand corner. So we're going to go in the reverse direction now. The reverse direction is going to be a little bit trickier. So let's once more remind ourselves about the powers of 2 as we are going on here. So 2 to the 0 we said was 1, and then every time we go on to the next exponent, we're doubling. So we got double that is 2, double that is 4, 8, and then 16, and then 32, and then 64. Here's where it starts to get a little tricky. 2 to the 7th, double 64 is 128, double that is 256, double that is 512, and double that to the 10th is 1024. So here's the way that we're going to think about converting from decimal to binary. We're basically going to imagine that we're sort of making change. Let's imagine that we had coins here, and the coins had values equal to a power of 2. So we have a 1-cent coin, we have a 2-cent coin, a 4-cent coin, an 8-cent coin, etc. But let's imagine that we only have one of each of these coins. So let's say we were trying to use these coins and figure out how could we make a dollar, or to think about this in a more directly mathematical, abstract way, how could we represent the decimal number of 100 in binary? Well, again, let's imagine that we had a bunch of different coins that were worth 1 cent, 2 cents, etc., on up to 64 cents, 128 cents, 256 cents, and so on. Well, clearly the 128-cent coin is not going to do us any good because it's more than what we want. So here, the biggest denomination that would make sense to take would be one 64-cent coin. Right. So that would get us up to 64 cents. We want to get all the way up to $1. So we're going to see what's the next largest coin that we can take. Well, adding on 32 cents will get us to 96 cents. So we could add on the 32-cent coin. So we're going to do that, one 32-cent coin. And then continue on in this process, right? That gets me to 96 cents. I can't take the 16 because that would take me too far. I can't take the 8 because that would also take me past $1. But if I took the 4-cent coin, I said it was at 96 cents, adding in the 4-cent coin, that would get me to $1 exactly. So we have one 4-cent coin. But note, in the process, we also said that there were not any. So there were 0 16-cent coins and 0 8-cent coins. And then we would need 0 2-cent coins and 0 1-cent coins. Okay, so now how do I take this thing that I just did? What does it mean? Well, here, I would need one 64-cent coin, which was worth 2 to the 6th cents. I would need no, sorry, excuse me, I said that wrong. I had one 32-cent coin, so I need 1 times 2 to the 5th. But I would need no 16-cent coins, so 0 times 2 to the 4. I would need no 8-cent coins, 0 times 2 to the 3. I would need one 4-cent coin. I would need no 2-cent coins, and I would need no 1-cent coins. So this is literally just doing the exact process that we did before, but in reverse. We're figuring out what are all of those numbers that are multiplied by the various powers of 2. So those values, let me change the color here, those binary digits, and this was a 1, those numbers are going to be the binary digits in my binary numeral here. So here we would have a 1, 1, and then 0, 0, and then 1, 0, 0. So this, as a binary numeral, represents, if we did the expansion, we take us right back up to here, right? This is the number of powers of 2 squared I have, and then 2 cubed, 2 to the 4th, 2 to the 5th, and 2 to the 6th. So I got 1 2 to the 6th, 1 2 to the 5th, 1 2 squared, and that's it. Now, it would be a little taxing to have to think about this all of the time, particularly if we thought about how we represent, say, $4 billion or something like that as a binary numeral. So there happens to be an algorithm for doing this. And it's going to be a little bit different than the algorithm that I just expressed above, but I wanted to present it as a different way of thinking about it. So here's the algorithm that we're going to talk about to convert from decimal to binary. And it's going to involve division, and particularly focusing on the remainder when we're doing division. So we're going to start with our number that we're trying to write as a binary numeral. We're going to divide it by 2. We're going to record the result, which is 50, and the remainder, which is 0. And now, like we often do with algorithms, like a loop, for loop, or a while loop, or whatever you have, we're going to repeat this process. And we're going to keep going until we get the result to be 0. So I'm going to take this number 50 and then divide it by 2. Why 2? Well, because it's binary. There's more I can say about this algorithm, but it's not really necessary to prove it to you in this class. So we get a result of 25 with no remainder left over. And if I try to divide 25 by 2, it doesn't divide evenly, right? I can get 12 out of it, but with 1 left over. So now I'm going to continue with this result, and we're going to take the rounded down result. So we're going to take 12, divide that thing by 2. I get 6 with nothing left over. Keep going. I'm going to take 6 and divide by 2. That will get me 3. Divides evenly, so nothing left over. Now 3 divided by 2, I can divide by 3 by 2 once with a remainder of 1. And now I'm going to take, again, keep going, continue the process with the rounded down result. I could try to divide 1 by 2. Well, it's not going to work very well, right? 1 divided by 2 is just going to get me nothing, but I'll still have that remainder of 1. So the last part of this algorithm is this process that we've just done. The digits of that binary numeral are the remainder, but the way that we read it is actually from bottom to top. So since we've already done this exact example, we're just confirming our result that we have here. Kind of feels like magic unless you see the proof, but this number that we have here, those numerals 1, 1, 0, 0, 1, 0, 0, that thing in base 2 corresponds to our decimal numeral of 100. Again, if you want to write that with a little base 10 down there to make it very clear that you're working with a decimal numeral, then by all means. Well, we can confirm this result with the base expansion because we actually already did it up there, right? So that process that just yielded that thing is going to get me that decimal numeral. So you'll note that going reverse is a little bit more challenging than just writing out a number in decimal. So this is going to be something that takes a little bit more practice. So that is all we're going to have left for this section is just to do a couple more examples like this to convert some decimal numerals into binary. So let's look at the number 172. Let's convert it into binary. And as a little bonus question, we'll ask ourselves how many bits are required to represent this thing as a binary numeral. So our thing said, we're going to take the number that we have and divide it by 2. I'll let you check this on a calculator if you like, but 172 does divide cleanly by 2. The result is 86. Of course, we knew it was going to divide evenly by 2, right? It's an even number. So it has a remainder of 0. 86 divided by 2 will get us 43, also divides evenly.